Cast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody, and this is Dr. Mansour, and today is July the 4th, 4th of July. Sorry to bring you on the 4th of July, but you promised me that you are going to do anything for the sake of the PE, so you are willing to sacrifice the fun and the time you spend with the family today, but I'm glad that I have about 16 of you today. That's good. That's good attendance. Just try to do your best, and you still have time. After you finish the class, you can go to the fireworks, and you still have from 4, because we're going to finish 4:15 or something like that. And you still have from 4 until midnight, so for the fireworks. So I will not really stop you from doing that. But as long as you do it safe and stay away from coronavirus, because today, as you heard the news, Florida, they have the record of cases today, thousands of corona infection. Okay, and so stay distance. Try to put the mask, 6 feet distance, all of the above. You are for sure you are memorizing this instruction that we are getting. Okay, so welcome to the last free civil workshop. Today is July the 4th, and I added this session, as you remember, because I missed one day, or I was not feeling well one day, so I made it up. So if you look to the brochure, and I'm going to have a new brochure, by the way, probably I will send it to you tomorrow. Still the same, everything is still the same except the seismic and surveying for the third quarter. So this was a free workshops. This is the civil. Okay, already we are done with that, and transportation we're done with that, and construction we're done with that. So I did all these free sessions as far as I know, except, as I told you, I missed one of these days, so I added the 4th of July. It was supposed to finish June 20th, but because of the but the rest of the brochure, okay, will be updated, including seismic and surveying for the third quarter, and it will be emailed to everybody, those who are already interested. As far as the regular classes, will start tomorrow. So tomorrow is the first day, which is July the 5th, and this is going to be transportation. Here it is, July 5th. Tomorrow, based on our website and based on the brochure, tomorrow is the first class, which is Sunday. I will be here tomorrow from 8:30 to 4:30 teaching the regular class. Okay, those who are enrolled the first time, I hope that you receive the materials. Sometimes we are short of materials. We are doing our best, especially with this pandemic, to get the books and to get supplies are really, really difficult nowadays for me. Especially, I do everything almost by myself, but I am doing all my best to help all of you. Forgive me if I am shortcoming. Sometimes I am not really fast to respond to your email or respond to your request, or we are behind. Forgive me for that. I know you need to pass. It's not your fault, it's my fault, but I will do all my best. I am up to date as far as scanning and sending all the notes until last week. I scanned 4 of them today and send it to all of you. If you did not receive any of these notes, please let me know. Also, I sent yesterday, and I sent it also today, the chapter I talked to you about it before, which is material chapter. This materials chapter, it is part of my book, of the FE book. Okay, I have the FE book, FE 7 book, and one chapter is chapter 9, materials. I found that this chapter is almost, I would say 98%, it is for the PE. Okay, there are a couple items here are not related to the PE. For example, the last section about thermal stresses, but I included just in case. Composite also, it is here, but you don't. So there are 2 sections here in this chapter: the composite and the thermal stresses. To the best of my knowledge, they are not included in the PE. So this is why I'm saying that almost 98% of the material that this was sent twice. It was scanned as a PDF, scanned it and sent it to you, scanned it as a PDF, but for some reason the scanner or the copy machine, for some reason, I don't know why it doesn't come very well. So I converted it from the Word and I send it to you. So you have both. In fact, it is a very healthy chapter. Is about 71 pages. 71 pages. Okay. So it is very healthy chapter, and I will do my best today to cover as much as I can. And so the regular classes will start starting tomorrow, and the following week is going to be the AM and so on. So the schedule is on our website for those who are enrolled. For example, transportation group, I sent them the ID yesterday. There is one ID. Okay, you need to join me. This ID is only for you. You are not, it's not free. You are not supposed to pass it to anybody. So I send it for those who attended the spring semester and those who are enrolled the first time. And if there is any update, I will let you know. But I communicate with you, and if anything I am missing, please let me know. The following week, which is 7/11, okay, 7/11. 7/11 is very important, by the way. 7/11 stores, okay. And 7/11, by the way, there is a table in chapter 7/11. Do you remember the table 7/11? Okay, always I joke with you, I try to remind you. 7/11 is a table, we're going to see it next week, okay, in the Civil Breadth Reference Manual, the thick book that you have, and in chapter 7, which is materials, by the way, and I started, okay, and there is a table here, it's called 7/11, and I told you this table is very, very important, and let me just bring it, and here it is, and it turned out to be 7/11, chapter 7, table number 11, 7/11, which is a soil weight volume relationships, all these properties of soil, and we'll talk about this next week, which is 7/11 also, 7/11, so Saturday. So I will start, as I mentioned before, I'm going to start where I stopped in the spring semester. Those of you who attended the course in the spring, we stopped because the NCESS canceled the April exam, and we discussed what options do you want me to go with, or do you recommend, or there were 3 options, option 1 and option 2 and option 3, and we discussed this together, and we ended with option number 3, which I offered it that I'm going to offer, we are going to stop. So we stopped, I believe, late March, okay, or mid-March, I can't remember what date we stopped. And I will offer series of free workshops to keep you intact with the material, and I did that. So tomorrow, okay, transportation will start where we stopped, and the AM also I'm going to start from where we stopped, and the same story with construction until I finish the course. And after that, I will start over again from the beginning. So for those of you who attended the spring, it is your choice. You would like to go back again from chapter 1, it is your choice. If you'd like to join me, you are very welcome. But we're going to start, at least to save time, I don't like to start from the beginning. And I know I'm going to start where I stopped in the spring until I finish the course. And after that, I will start over again from the beginning. And for those of you who attended the spring semester, you are very welcome to attend again. And for those who attended the first time, we will be continuation of the course, at least to get the maximum. I am looking for what is the maximum benefit for you. This is what I'm looking for, okay? So if you have any questions, you are very welcome to send an email to me, and I will do my best. So this is the 7 a.m. If you have any requests, send an email to me. I know one of you is raising the hand right now, but it will be very difficult for me to remember everything. So I will try to do my best to make the discussion. No, I did not send it, my friend. I will not forget. Okay, I did not send the ID yet for the 7 a.m. No, the only ID I sent so far, it is the transportation PM, which will start tomorrow. Transportation PM. I have it, but normally I wait until maybe somebody will enroll next week, so I will not forget. So you will get it. You will get it. Okay. And always, if you have any problem during the lecture day, give me a call. 559-289-6412. And normally I keep my cell phone here next to me, and I keep it on for the first 10-15 minutes, and after that I turn it off. Just the first 15 minutes. If somebody has a problem with the ID, he cannot log in, he cannot join, he has a problem. So this is my cell. You are very welcome to call, but for sure you will get it. You will get it, but it will not hurt to remind me if I forgot. Okay, so having said that, let's start. So this chapter, as I told you, the chapter materials. So these are the topics for the FE civil, the fundamental engineering civil. Okay. However, I go beyond that in order to cover more as far as the PE. So the first one, for example, thermal and mechanical processing. I was asked last week a question about the effect of carbon content on the properties of steel or properties of the structural steel specifically. I will go over that. We have something is called cold working. What is cold working? Steel produced two different ways. Okay, cold working. Okay, it is a plasticity deforming. There is a picture on the following page, and this under this figure here, figure 9.1. This figure here, let me just get something here very quick. At least I can get the maximum benefit of the time. So there are two methods or two ways to produce steel or structural steel in general. So it's called the production methods. Production methods. We do have the hot and cold. Hot working or cold working. I need you to know the difference between these two, just in case if they ask you what is the effect of the cold working on the certain properties. And you will find that this is shown on the figure I'm going to show you, that the cold working, it does increase certain properties and decrease certain properties. So, for example, if you look to figure 9.1, figure 9.1 in the front of you here, this is the cold and hot rolling, working or rolling, okay, for steel. And associated with this illustration here, a very important curve, we call it a stress-strain curve. Stress is sigma and the strain is epsilon. Stress is equal P over A, as we are going to see in just a minute, and the epsilon is equal delta L over L, change in length over length, delta L over L. And he gave us here, okay, series of curves, okay, and you can see from these curves very important parameters that is going to be, it could be a target for a question. So the first curve, I will make it blue, and let me, okay, which is the hot rolled steel. Okay, if I use different color here for the cold work steel, the green and the blue, this is cold and this is hot. And probably you heard the term hot rolled steel and cold rolled steel. Because steel production, they start, for example, with a certain diameter or certain shape, and they would like to produce a smaller diameters. These wires that we see, these reinforcing bar with different diameters, a plate with different thicknesses, and so on. So they squeeze the material between rollers. These rollers will produce whatever diameter I need and whatever thickness I need from plate under very high pressure. So if the steel is going to be hot while we're doing this process, we call it hot rolled steel. If the steel is cold, we call it cold rolled steel. So the steel that will be processed to produce different shapes and sizes, it could be either hot or cold. And this is explained here, hot rolling and cold rolling. That the principal rolling process are hot and cold rolling. Okay, hot rolling is the most common method for refining, okay, and cast structures and so on, so and so. And I need you to I needed to read this just in case, as far as the concept. But the most important thing, in addition to the description of the cold and hot rolling process, the hot rolling and the cold rolling, is the stress strain curve. The stress strain curve, as you know, is a criteria that we use it, or the condition or the shape, that it's going to dictate a lot of things as far as design. As a designer, you select a material, it does have certain properties. So one curve that we use it a lot, and this is true for steel, for concrete, for aluminum, for wood, name it, for structural materials in general or construction materials, we are using this relationship to select the design parameters. So this is epsilon, which is delta L over L, and this is sigma, which is equal P over A. So if we look to the hot roll steel, the steel that has been formed while it's hot, you will find that the curve is like this, and I use a blue. Let me use a blue color here, which is this one here. It will be like this. This is a hot roll steel. The slope of this line is called E, which is Hooke's law, which is sigma over epsilon, which is the modulus of elasticity. We said that this number is 29 million psi, or 200 GPa, gigapascal. Also, we need to be familiar with SI units, because sometimes they ask problems, and as far as I know, the exam is dual units, so we need to be familiar. Where 1 megapascal, 1 MPa, is equal 145 psi. And giga is 10 to the 9th. So if you take this, multiply by this, will give you exactly 29 million psi, or 29,000 ksi. We have something is called upper yield point, lower yield point, F sub u. We have something is called F sub y, which in the steel manual call it F sub y, which is the yield stress. F sub u is the ultimate. And if you open the steel manual, and I'm sure that you look to the steel manual, and you'll find that under the design parameters, which is the second chapter, general design consideration, you will find the table that I showed you 10 times. This is number 11. I'm counting, by the way. I remember how many times did I show this table. Oh my God, no. Okay, so this is the steel manual. This is the table that applicable ASTM specifications for various structure shapes. For example, A36 steel, carbon steel, A36. Okay, if I get closer to this, you will find that for the A36 steel, you will find that the F sub y, which is the minimum yield stress, is 36 ksi, and the ultimate, or the tensile strength, F sub u, is between 58 to 80. And this number must be given to you in the exam. And different types of steel, A500, 540, 551, different types of steel, they are listed here in the ASTM, listed here in the steel manual based on the ASTM specification. ASTM stands for American Society for Testing and Materials. This is the testing agency that we are talking about. So this is for structure shapes. They have also the ASTM for plates and bars, and they are asking what is available, what is not available. And normally we look to this before I order steel, and to make sure that the steel I'm going to order for my job is available, commercially available, and so on. So the F sub u, which is a tensile stress, and F sub y, yield, they are very, very important. They are very, very, very important. Okay, so, and they specified by the codes or the ASTM, as you know. So this is how to, okay, this here, we'll call it a strain at failure. At failure, or failure strain. And if you remember, we did this through the testing, the specimen, which you are going to see it shortly, I think, and we are applying the load and establish this relationship. If we look to the second curve, which is the cold roll steel, you will find that, number one, the modulus of elasticity doesn't change. Okay, so this is the first thing that I need you to know. So the modulus of elasticity, let me use the green also. Okay, so the modulus of elasticity will be the same. It will go the same here, and it will go up, and it will come like this and stop here. Okay, probably the yield is not well defined. Make it a little sharp, a little bit sharp transition from here to here. This what is known as cold rolled steel. So which is a better drawing here. It is figure 9 now, and you can see here I wrote something. Cold working increases the yield, the ultimate, but reduce ductility. E is the same. I need you to know that. And all these could be a target for a question, okay, related to materials. Which of the following is true about the cold working? Which of the following true is about the hot rolling? Okay, which property will decrease or will increase by the hot working, or name it. But as I know, as you can see here, E is the same. Modulus of elasticity is the same. This is why I'm saying that any civil engineer, do you remember the joke I told you? Even while he is dying, if we ask him about the modulus of elasticity of steel, he's supposed to answer 29 million psi. So it doesn't change with the type of steel. Okay, and cast iron is not steel. The difference between cast iron and steel completely different. So the cast iron has a different modulus of elasticity E, but the E steel is constant number, and this number is a 200 gigapascal or 29 million psi. So E is the same. It doesn't matter hot or this way. The slope of the line is the same, but the yield will go up with the cold working. Ultimate, which is F sub U, will go up, but ductility will go down. Ductility, as you can see here, this is the strain at failure, and this here is strain at failure. So you'll find that became more brittle. Okay, ductility decrease means, i.e., more brittle. And we have an issue with the brittleness of steel, by the way, because we need the steel to be ductile. The steel in general ductile. And if you are talking about ductility in general, this is a ductile material. This is a ductile material compared to aluminum, for example. Okay, or compared to concrete, for sure. But we are saying that this is more ductile than this. This is more brittle than this, relatively speaking, within the same category. So I need you to know that. So ductility is very, very important, especially in seismic design, because we have an area. The area under the entire stress strain curve, which, for example, for the cold, okay, compared to the area under the stress strain curve for the hot, you will find that the areas are different. In fact, more area means more toughness. Toughness, which is the total area under the stress strain curve, and this toughness is indication of the amount of energy that can be absorbed. The higher the energy, the better, obviously. The higher the energy, the better. Okay, and this is what we are looking for it, especially in seismic design, for example. Okay, and we will see that. So so I need you to be aware of that, and anything I wrote here, okay, I did my best in order to alert you about the effect of the cold, and followed up with the question. Okay, cold versus hot rolling for steel. Okay, which of the following is true about cold working and hot working? Hot, cold and hot. Okay, hot. This is R rolling, ROLL, hot and cold, or cold and hot rolling. This is a typo here instead of tolling, rolling. So this T, okay, rolling steel. Number one, cold rolling increases the yield and the ultimate. That's true. The most of elasticity for steel is constant in hot and roll. That's true. Cold working for steel lowers the ductility, and the steel becomes more brittle. That's true. This is why I say all of the above, and the answer is D, which is in agreement with what I just told about. Okay, so we need to know that there is some kind of correlation between the effect of the production method here we're talking about the cold versus hot rolling or rolled steel with the carbon content. I need you to be aware of that. And this is one of you asked me this question, I believe last week, and I said it's coming. And if you flip the pages and go to page 6, please. Page 6. Since there is some kind of analogy between the cold working and the carbon content. You will find there are 3 graphs. This is figure 9.5. This is on page 6. Everybody with me? I hope that all of you have the document. You print it, and I encourage you to print it and take it with you to the exam, just in case. Maybe they ask you a question. You will find that we have, again, a stress-strain relationship. I define the stress and the strain one more time. And here we have 3. We have 1 here, which low carbon steel. And this is the medium carbon steel. And this is high carbon steel. As we increase the carbon content as a percent. Don't worry about how much is the percent. Don't worry, I doubt they will ask you exactly how much is the percentage of the carbon in the steel. It's available. I can give it to you if you want. But anyhow, I need you to know that as the carbon content increases, okay, the same. The toughness, as I told, toughness is the total area. And there is another term, by the way, we use called resilience. Do you remember resilience? What is resilience? Resilience is the area under the linear portion of the stress-strain curve. Okay, resilience. And we need this, by the way. Sometimes we need this in order to calculate the elastic energy. So the area under the linear portion, this triangular area here for the first curve, this one here, this is called elastic energy. Elastic energy. Okay, elastic energy. Or we call it resilience. Resilience. In fact, the elastic energy, let me write it here, that the resilience / elastic energy, or elastic strain energy, by the way, sometimes we call it that, strain energy, is equal what? What is the area of a triangle? Is 1/2 base time height. This is the strain at the end of the elastic range. So it is epsilon times sigma, and sigma is this one here. I can substitute, because I know over this linear portion, I know the relationship, this one here, that I know that E, which is a moments of elasticity E, is equal sigma over epsilon. So I can say epsilon is equal sigma over E. So I can say that this is 1/2 sigma square over E. And probably you saw this equation before, that the elastic energy is 1/2 sigma square over E, moments of elasticity. And sigma, it should be supposed to be the yield, the sigma at the yield here, or the F sub Y, whatever is given to you. So elastic strain energy. So going back to the carbon content, so we have 2 terms, toughness and resilience. Resilience is the elastic energy, and the toughness is the total energy. So as the carbon content increases, steel becomes more brittle. Modes of elasticity E is still the same, by the way. E is the same. E is the same. But as we can see here, you will find that the curve is, and the area, as you can see, start to decrease. So as carbon content And this is the question number 94. Which of the following statements is not or are not true about the effect of increasing carbon content? Which of the following statements is not? He's asking for only one. So is not. The effect of increasing the carbon content. So as the carbon content increases, carbon content or percentage increase, what is happening? The yield will go up. Yes. The ultimate strength or tensile strength will go up. Yes. Ductility will go down. Yes. Increase in the muscle elasticity. No. So this is yes, yes, and yes. True, 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 and this is not true. So the answer is D, and this is what I selected D. So we need to be aware of these questions, and there are many, many ways they can ask these questions. So please do your best in order to understand the. So there is a correlation between, or there is some kind of analogy. Let me put it that way. Analogy, much better word. Analogy between the production method and the effect of the carbon content. As we increase the carbon content, you'll find that some properties will go down, some properties will stay the same, and some properties will go up. So we need to be aware which property will go up or increase, which property will go down or decrease, and which property will stay or constant. Okay, that's what I need you to be aware of. Okay, so I will go back again where I stopped, and a lot of reading I will ask you to read. Okay, here we have mechanical properties. When we do the testing in the lab, okay, we develop mechanical properties like strain and stress. So if we start with strain, they are using the Greek letter epsilon. Epsilon. Okay, and epsilon is equally change in length over length. But here there are two of them. We have something called engineering strain, and one is called the true strain. They are using epsilon sub t to indicate the true. And the engineering, they leave it like this, epsilon. Okay, when we do the testing in the lab, and we have this specimen here, which is a tensile specimen. Let me bring it one more time. Or let me bring a different specimen. This is after failure. I have a lot of them here. This is the specimen before failure. Okay, different diameters, but we will follow ASTM, by the way. Okay, and this is after failure. This is the specimen start to nick down, as you remember in school, and eventually it will fail when we reach the failure strain. But before we do the load, or before we do the test, we mark here. We mark something called gauge length, normally 2 inches, with a center punch. Make a little tiny dot here and a little dent here, 2 dents. The distance between them is exactly 2 inches. We call it the gauge length. And after failure, we measure, by the way, the distance between these 2 dots. They are here, by the way. You can see. I don't know if you can see them. Here it is. This little tiny dot. This dot here. So this is how we determine the failure. So the question is, when we are saying that a strain, which is epsilon is equal delta L. Delta L is the change in length. You divide by the length. Which length? The original length or the instantaneous length? Because as we apply the load, the distance between these 2 dots is changing. Okay, so they came up with 2 definitions. One is called engineering and one is called true. And I will tell you which one is larger and which one we use it in real life. So there are two definitions for strain, engineering and true. The engineering is referring to L sub O, where L sub O is the initial length. Okay, this is a specimen. Try to draw one very quick. Sorry, my specimen is crooked a little bit because of corona. This is not effect. This is not me. This is the effect of corona. Okay, no problem. Okay, corona will be over. Don't worry. Don't say because I start to hear rumors among the engineers. One of the called me, Dr. Mansour, did you hear that they are going to postpone the exam in October again? I told him, no, I did not hear that. I told them why. He said because of corona. I told him, look, my friend, don't really slow down, please. This is why I offered. I used all my summer, and even my family was against that. Why I kept myself busy during summer to have all these workshops, except Ramadan. As you remember, Ramadan I was fasting, so I kept you, at least I needed to keep you at the same speed, to keep you in the same mode. I don't like to slow down. If you hear any rumors, this is fake news. Okay, don't listen to fake news. Fox News, oh my God, now we're talking about CNN and Fox. No, the PE is coming. Okay, the exam is coming October 22nd, October 22nd and 23rd, 2 days this time because the cancellation of April exam. So they are going to offer the exam on 2 days, on Thursday and Friday. It depends what is your PM, transportation, construction. Check with the NCESS, anything related to that. But if I were you, I will keep the same speed. The preparation is very important. Prepare and prepare and prepare. God forbid, and they came to the October exam and they found that there is no way they can have the exam and they are going to postpone it till April 2021, you didn't lose anything, but at least I should be ready. I need you to be ready, okay? So don't hear the rumors from all these news, Fox News, or CNN, or fake news, whatever you like to call it. Make sense? I'm not a Republican or Democrat, by the way. Okay, just, okay. So going back. So we make a dent here and make a dent here at the beginning. This, we'll call it gauge length, L sub O. But if you look to the true, they are dividing by L. The L here, they define it, by the way, in the NCESS as the initial length. And initial length. I disagree. This is from the NCESS. I put it that way for a reason, because the NCESS is the only book that FE people will see it. I told them they should change. This is the initial length, yes. This here is supposed to be the instantaneous length. Instantaneous length, which is the moment. At the moment that we're recording, delta L was supposed to measure L. But here we are dealing with this normally 2 inches. For you, it will not make too much difference, okay? Because as I told you, this is only for the FE. So I define it here, and I use the actual length, which is instantaneous length. And by the way, epsilon sub t is equal ln times 1 plus epsilon. So the engineering and the true, this is engineering strain, which is delta L over L sub O. Okay, and this is what we use, by the way. Usually use in design. I will tell you why. This we don't use it in design for 2 reasons. I will tell you why in just a minute. So this is the one we are using. It is easy to determine the gauge length at the beginning. The instantaneousness, yes, it can be measured in the lab, which will be difficult, but I don't like you to be concerned about this too much because we don't use the true strain in our real life. Okay, so this equation we can divert. Epsilon sub t is equal ln 1 plus epsilon. Again, there is no need to derive equation. Ln, it is this log to base e. As all of you know, natural logarithm. So I have a question 9.2. Which of the following is true? A true strain is always equal engineering strain. A true strain is always less than engineering strain. A true strain equals engineering strain only for small values of strain. For small values of strain, and a true strain equals engineering strain only for larger value of strain. So again, conceptual questions are very, very important during the conceptual questions. And conceptual questions, sometimes they are difficult because the wording, probably they are using better English than my Egyptian English, but we need to be careful with the conceptual questions because one word can make a difference. So if you look to the value of strain, so epsilon, which is the engineering definition, engineering, is equal delta L over L sub O. So the change in length over the original length. Let me ask you a question, and I'm sure that you have a calculator, and they will give you only 22 seconds to do that. If I have A36 steel, this is epsilon, and this is sigma, and I have, normally the design stress strain curve is like this. We ignore this hump here. This is the upper yield point, and this is the lower yield point. This is the upper yield point, and this is the lower yield point. And this is what is the F sub Y. In the steel manual, they don't report the upper, they report the lower. Because the upper yield point is a temporary one for a short duration. So we don't rely on it in design. Okay, so I need you to be aware of that. The upper yield point is not really recognized as a design parameter. Okay, the steel manual, they adopt the lower yield point, which is F sub Y. So if I have A36 steel, this strain here, we call it epsilon sub Y, yield strain. And this is F sub Y. And if I have A36 steel, can you give me the value of epsilon sub Y? How much? This value? And this is inch per inch, by the way. Strain is inch. I need a number here. I will give you only 1 minute. You have calculator, always bring your calculator with you. The two calculators they are going to use on the exam, I need you to be aware of that. I need you to do it. Otherwise, you are not going to be, okay, in big trouble because you will take me to lunch 10 times if you. Okay, it seems to me that we got some answers. That's good news. From its name, by the way, A36 steel, from the name A36 steel, if you go to the steel manual, you will find this value here is 36 KSI. F sub Y, 36 KSI. He should give it to you, by the way, but I didn't give it to you, at least to remind you that the A36 steel gets its name from the yield. And since I know the slope of this line is E, which is the modes of elasticity E, this is epsilon, and this is sigma. So Hooke's law, this, by the way, Hooke's law, Professor Hooke's law, E is equal sigma over epsilon. So I need epsilon sub yield, so is equal sigma sub yield divided by E. So right now, sigma sub yield is 36 times 10 to the power 3, and this is PSI. divided by what? What is the most of elasticity E? Do you remember the number I told you that any civil engineer has to remember that? Here it is, 29 million PSI. If you do the simple calculation with 36,000 divided by 29 million, you'll get a number, and this number is very small. And I will tell you, okay, right now what's meant by small strain epsilon. So this number here is 0.00124 inch per inch. Agree or disagree? If you agree, that's good news. If you disagree, don't take me to court. Let me get the answer from one of you, at least, okay? So it is 0.00124. Okay, thank you very much, Alex. Okay, so, and Francis. Okay, thank you very much. So this is strain. At the yield, we call it yield strain, and this is very important, by the way, in design. In design, we need to know what is the yield strain, because for concrete structures, we need to make sure that the concrete will not crush before the steel yields. I need the steel to yield first. I need the steel to yield first. At least it will give us a warning. If you have a beam, concrete beam, reinforced concrete beam, and it has the rebars here, I need this beam. If the beam is overloaded, I need this beam to yield. What does it mean, yield? Mean that the beam will deflect as this. It will go, will deform. It start to sag down. This will give us a warning to run away. This is called the ductile type failure. Failure, there are two types. Failure, from the structure point of view, there are two types. One is called ductile or ductile, as the British pronounce it, and one is called the brittle. Brittle failure, this is called sudden failure, sudden failure. Sudden failure. Sudden failure, God forbid, like somebody who passed away suddenly. Everybody was shocked. Oh my God, did he pass away? Without warning, but here, ductile is slowly, he was sick. And after that, he got sicker and so on. So this ductile type failure, this is a slow failure, or failure with warning. With warning. He was sick. Sorry, I'm using some analogies that try to. So I need the beam start to sag down. Oh my God, and not, oh my God, the beam start to sag down. Why? Okay. But the brittle type failure without warning. This is sudden failure without warning, we are sitting drinking coffee, or we are sitting in your room studying for the BE, and suddenly the roof collapses on us without any warning. This is called a brittle type failure. We don't need that. We need warning. We need warning. So this is not the desired. So in design, we are ensuring that the ductile type failure will occur, where the steel will reach the yield first before the concrete crushes, because concrete is a brittle material. Okay, so anyhow, so this yield strain is very, very important, as you can see, which is epsilon sub y, which we just calculated for A36 steel. Is this a small number or a big number? Do you remember the equation? It says epsilon sub t is equal ln 1 plus epsilon, the true strain, and this is the engineering strain. Let us take this engineering strain. Let's assume that 0.00124. So this is ln 1 plus 0.00124. I need somebody to give me the number to see what will be the value in epsilon sub t. Go ahead. Okay, so it is 1.00124, and all of you have the calculator. Ln, what did you get? 0.00129. Is this correct? Can I say, oh, this is okay, it's 0.00124. So in this case, over this is the elastic range, by the way. This is from here to here, all the way to elastic. So the engineering strain and the true strain are essentially the same within this range, or over this range. And this is why engineering strain is the one we are using because it is easy to calculate in the lab, and there is no difference between the engineering and true. This is why we're using the engineering definition. I need you to know that. And as you can see, this relationship, so they are equal for a small amount of, this is called a small amount of strain. So I need you to be aware of that. And this is why, okay, I selected the answer C for question number 9.2, that the true strain equal engineering strain for a small values of strain. The answer is yes. So this is true. Which of the following is true? Be careful during the exam. Okay. The same story with the stress. We have something that's called engineering stress and the true stress. The engineering stress at the beginning, before we apply the load to the specimen, we measure the diameter with the micrometer. Do you remember the micrometer or the caliber that you used in school? Okay. So the one that has a vernier scale, I don't know if you saw that, or they are using the digital nowadays. Okay. We measure the diameter because the area cannot be measured. The area can be calculated only, okay, for something like that. So we measure the diameter, and from the diameter we can get the area. The area is equal to pi d square over 4, or simply it is pi r square. Which area are we talking about? Or the original area, which is this one here, the initial cross-sectional area, or something is called the instantaneous actual cross-sectional area, which they call it A. Because as we apply the load, the diameter is getting skinnier, smaller, smaller. Which area are we talking about? The original or the instantaneous or the actual? The actual or the instantaneous one? Again, we are using the engineering because essentially almost the same. Okay, there is no difference, and we talked about that. And here we go. If you flip the page, this, do you remember this equation? Hooke's law? Here it is. Hooke's law. I need you to know that. Modulus of elasticity, by the way, we call it Young's modulus, by the way, or modulus of elasticity. Okay? So modulus of elasticity or Young's modulus. This E, this modulus of elasticity E, okay? The slope of this line here, E, which is equal sigma over epsilon, which is Hooke's law. This we call it, sometimes we call it Young's modulus. Young's modulus. Professor Young, he is a British, I think a British scientist. Okay, so I needed to be aware of that. So please read this. Okay, all these things. Okay, and some key mechanical properties obtained from the tensile test: elastic modulus, ductility, ultimate yield, all these things we talked about. Here it is, the true strain and the engineering strain, or the engineering strain and the true strain. And this is what we normally use in design, the engineering definition, because it's dealing with the initial area, the initial cross-section area. It is easy to measure. Here we're talking about the instantaneous, the word instantaneous, here it is. Instantaneous, or the actual cross-section area. And here is the modulus of elasticity, Hooke's law, modulus of elasticity, a function, so and so, and units, megapascal or gigapascal, all these things. Here are stress strain curves, the actual one and the design. This is the design one. This one here, the typical design stress strain curve, modulus of elasticity. But if you look to the actual, you will find that we do have a proportional limit, yield, tensile, elastic, fracture, strain hardening, plastic zone, elastic zone, all these things. This is epsilon. I prefer to call this is sigma. For some reason, ended with F here. This sigma is equal P over A. Okay, but before I proceed, let me see. It seems to me there is a question from one of you. Forgive me, my friend. I saw you raising the hand, and you are very welcome to raise your hand. And in this case, I will unmute you, and you can speak out. So, Alex, you are in the air. Go ahead, please. Alex, yes.
Yeah, 836 steel is, that means, for example, you have 834 steel, it means the yield stress is 34. It has something to do with that?
Okay, let us get the Bible. The A36 is is the only one, and let me show it to you, because it's very common use. So, or we use it on a daily basis. So let me bring the graph, the one I showed to you before, and this will answer your question, my friend. Go ahead, please. And let me get closer and closer and closer. I need you. Okay, I will look to the two tables that I showed you before. Okay, the first one,
Oh,
this
okay.
is ASTM for various structural steel. A36, this is 36. Do you see that? Let me just make it focus more.
Yeah, I see it.
Okay, yeah, sir. Okay, let's. Which one you are talking about right now? Which one?
Okay, I thought it was any correlation between that and the yield strength, but
No,
obviously it's not. Okay.
no. The only one, for example, A500 carbon steel or A529 or A501. Okay, but the A36 steel is the only one that this number matches. Is called A36. For example, A53 grade B, this is 35. Okay, so it's not a correlation, my friend. Okay, if you go to, did I answer your question?
Yes, thank you.
Okay, but be careful again. Let's go to the second page. Okay, it should be given to you in the, either you have the steel manual. Okay, if you look to the second one, okay, you will find for the plates and bars, the A36 steel, it could have a yield of 32, by the way. Okay, and at 36, you will find that we have some solid. We have a black here and here. The black here, it is okay, a preferred okay material specification. Okay, and other applicable. So it depends on the bar diameter and so on. So I will consult this steel tables, but the A36 steel is, it gets its name from the 36 KSI, but the rest are not. Makes sense to you?
Yes.
Good. And it should be given to you, F sub Y and F sub U. Normally, unless you are required to take the steel manual with you to the class, and you are required to carry it as one of the references, they are not obligated to give it to you. But for the AM, because this is the AM class, you are not required to take any references with you, because they're supposed to give you all the information related to the question. Okay, so going back to the, let me mute you again, my friend, so at least you can take your, okay, here we go. So the figures shown in the front of you here, figure 9.2 and 9.3 and 9.4, those are typical stress strain curves. However, I need to talk about this here. Some materials, especially the low carbon steel, like the A36 steel is a low carbon steel, by the way. You will find that the low carbon steel materials, they have the well-defined yield point. They have this hump here. If you look to this, you will find that it goes like this. If you exaggerate this here, this knee here, you will find that you have an upper yield point and lower yield point. And as I told you, this is the upper yield point, which we don't use it in design. We are using this lower yield point. The designer and the steel manual, they said that we are not going to rely this, because this is temporarily and is not really permanent one. So they take, which is this one here. You can see here, this is the F sub Y. So what happened? They ignore this. They ignore this hump that they go up and down. They smooth it out for us. And they ignore, because this is a temporary one. But as the carbon content increase, and we're going to see this curve again, okay? As the carbon content start to go up or to increase, you will find that the transition from the elastic to plastic is not really well defined. It is a curve like this. And this is what with the material that have a high carbon. So in this case, the curve is like this. It goes like this. And there is no well-defined knee. It will go smooth like this. This is for high carbon steel. High carbon steel. And also this is true also for cold working. cold working steel. They have this. So where is the yield? What is the yield? Where is the F sub y? How the steel manual decided the F sub y? Because it doesn't have this hump. It doesn't have a well-defined yield point. This not well-defined yield point. So they came up with what is known as the offset method. Offset. And I'm sure that you remember this term from school. It's called the offset method. Offset. Offset method. What is the offset method? And they agreed, by the way, ASTM, the American Society for Testing and Material, they agreed on 0.2% offset. Okay, 0.2% offset. I don't know if it's mentioned here or not somewhere. Okay. What is the 0.2% offset? 0.2% is steel. Is a strain. We're talking about steel, but is a strain. So the 0.2% offset, it is amount of strain of 0.002. So they are telling us, Mr. Mansour, for type of steel that does not have a well-defined yield point, and when I scan these things and send it to you, I need you to look at it, and if you find a typo or a mistake or an error, let me know, please. I can make a correction and proceed. So if this is epsilon and this is sigma, so for a material does not have a well-defined yield point, it is straight within the linear portion with the elastic, and after that is a curve like this. So there is no well-defined yield point. So they said we are going to move along the x-axis. Amount of 0.2% or basically is 0.002. And I will come and they draw a line at this amount of strain that's parallel to this one. So this is parallel to this. This will intercept with the curve, and we define, or they define for us, not we. Okay, they define this as F sub y at 0.2% offset. This is the way they do it. And they agreed on that, and they adopted, and the specifications call for that. So I needed to be aware of the 0.2% offset. So basically 0.2%, you are moving along the x-axis like this point C here. Materials do not have a well-defined yield point as high carbon steel. So in this case, they are moving amount of strain, and they agreed on the 0.2%, and they draw a line parallel to this. This will intercept, and after that, they move horizontally, and they define this is the F sub y. It's called the yield stress by the offset method. I needed to remember that, just in case, Okay. Okay. Flip the page, question number 9.3. Which of the following is true? A true stress is always equal engineering stress in tension. A true stress is always equal engineering stress in compression. A true stress is always smaller than engineering in compression or larger in tension. If you look to tension and compression, if you have a tension, this is P, this is tension, or the tensile test, according to ASTM E8, by the way. I believe E8, ASTM E8, yes, ASTM E8. If we do compression test for steel, also we apply, we have a cylinder like that, and we can Normally we don't do it. We do tension, but compression could be done also. This is a compression test. Here, the area A is getting A sub O is getting smaller. Here, the area, the A sub O, is getting bigger. So when we are saying stress sigma is equal B over A sub O, okay, this is the engineering definition, by the way, where A is the original area. As we start to apply the test, for tension, you are dividing by a smaller number because the area is getting smaller. For compression, you are getting area bigger. You are dividing by a larger number because the diameter is getting bigger and the area is getting bigger. And this is why, if we would like to draw the stress strain curve, and let me do it for tension and compression, you will see it like that. This is epsilon and this is sigma. So up to the or within the elastic range, they are essentially the same, by the way, almost the same. But it start to deviate right now. For compression, it's like that. For tension, it's getting like that. This is tension, and this is compression. This is for what? For the true definitions, true. Because as I told you, for the tension, you are dividing by a smaller area. So the stress is start to be larger. For compression, the area is getting bigger. But within the elastic range, this is called the elastic range, by the way, elastic stage / elastic range. They are essentially the same. Okay, the sigma engineering and the sigma true, they are essentially the same. Okay, like also the true strain and the engineering strain. And since we are using the engineering definitions, so we prefer to use it because it's much easier and there is no difference. So for compression, the true is getting smaller. For tension, the true is getting larger than the engineering definition. So, and this is why I selected the answer. Okay, let me flip the page. No, it is the same here. Question number 93. So in this case, which of the is true? I selected the answer D. The true stress is larger than in tension. That's correct because you are dividing by a smaller area, and this is why we selected the answer D. Okay, so look to the other two curves, by the way, are shown here. That's figure 9.5. This is toughness. Do you remember toughness? Here it is, toughness. Okay, toughness. Difference between brittle and ductile. Okay, large toughness and the smaller toughness. Ductile and brittle, which is related to. So please read these things and. Okay, so let us take a few minutes break and come back with open mind and open heart, get some fresh air, and after that we'll come back to talk about the other mechanical properties, and we will see what can we do. So let's take about 10 minutes break. Right now is about about 2:15. So let's come back at 2:25 with open mind and open heart and try to enjoy your break, and I will see you after 10 from now. Thank you. Okay, welcome back, everybody. Sorry, it took more than 10 minutes. Sorry. Okay, so how is everything going? YC is wrong. YC is wrong. Let me see if there is a typo. Okay, Max, you are telling me sometimes when I write the questions, I can. Let me minimize the window here. Okay. A true stress is always smaller than the engineering stress in compression. This is correct statement, by the way. A true stress is larger than engineering stress in tension. Let me see if there is another key word here. This has always, and this is not always. Okay, this is probably the reason. Here is always mean that it is within all stages, with the elastic stage and the inelastic stage. This is why the word always indicating that from the beginning to the end. This is why the answer C is not true 100% or is not correct 100%. But this is true 100%. Okay? Because of the word always is missing here. This is why answer D is the best answer. Okay, my friend? Okay, good. Yeah, one word can make a difference, and I hope that this is convincing you. If not, please let me know. Yes, okay, that's good that you see, agree with me. I'm afraid to go to court. Even anytime disagree with me, oh my God. Okay, so please look to these things and let me know. The following is creep. Creep, by the way, is one of the topics for those of you who took concrete design, and especially. Yeah, if you pick any concrete design book, like this book here, which is Reinforced Concrete Design by Wang and Salomon, and there is another author added recently, but Wang and Salomon, the original author, because I used Wang and Salomon was an undergraduate and the graduate, and the reason that Wang and Salomon, okay, because Professor Wang is a professor of my professor, by the way, in Wisconsin. Okay, University of Wisconsin Medicine. Okay, Professor Wang, Che Wang, he was a professor of my professor. Both of them passed away, by the way. My professor and Dr. Wang, obviously, both of them. So I still, and they are the best. They have, Wang and Salomon, they have a steel design book also. I don't know if you use it or not in the undergraduate. Oh my God, or a graduate, it is fantastic. So Reinforced Concrete Design and the steel design, both of them by Wang and Salomon, they considered they are among the best. I don't like to say they are absolutely the best, because there are many books available in the market. But anyhow, so I'm still more inclined, because he is a professor of my professor, and this is what I use in school, by the way, because during school, my professor, okay, or my doctor trainer, he always assign the books or select the books, okay, by Wang and Salomon for steel and concrete design. They have very, very good books. And now, so if you look to any book, it doesn't matter. Oh my God, I am so lucky. I open the page and it says creep. Okay, creep and the shrinkage. A creep and the shrinkage is a serious issue in concrete design, by the way. Okay, so what is creep? Okay, what is a creep? A creep is defined as deformation under constant load over time. This by definition. And I'm sure that you did a creep test back in Las Cruces, New Mexico, when I was teaching. We have a creep test, and I don't know if in your school you have such thing or not. A creep. So what is creep? A creep is deformation or elongation but the word deformation much better. Over time, under constant load. This is the basic definition. And I believe probably I put it here. Okay, something very close to this definition. Definition of creep. A creep is defined as time-dependent deformation at elevated temperature under a constant load or constant stress. Okay, so this is the definition of creep. They found that the concrete beams, this is why the creep is discussed very in depth for concrete, and there is a lot of research. When I was doing my PhD, there was a lot of research about creep and a lot of PhDs and a lot of masters about the creep. They found that over time you have a concrete beam, okay, either in a bridge or in a building, and this concrete beam over time start to sag down. It start to sag down like this. It's not deflection. Deflection, we calculate deflection, but this is a creep, which is deformation over time under constant. We need to know how much this creep, this deformation, how much, because this is over time. Over time is very, very important. It's not immediately or instantaneously like settlement. As you know, settlement, there are two types of settlement, as we discussed also in foundation. Settlement, and we discussed this also in the AM. Settlement, there are two types of settlement. Immediate settlement, immediate, or we call it short term. Okay, the one that's happening for sand. And long term settlement, okay, long term settlement, okay, which is over time, which is due to consolidation. Consolidation, which is mainly because of silt and clay, specifically clay. But this here is sand / gravel, because they don't have consolidation properties. So the same story with the creep. The creep consolidation will take over time also. It will take place, or the deformation of the clay layer will have in 10 years or 15 years. And if you remember the five mini exams that I sent you over the summer period, I don't know if you get a chance to solve all of them or not. Mini exam number 1, mini exam number 2, I think they were 5. Okay, so please let me know if you did not get the solution. I'll be glad to send you the solution. I believe I'm done with them. And they scanned and they are somewhere. Yes, so the mini exams, 5 mini exams, each one is 25 questions, about 25 questions. So it is about 125. This is during summer to keep you busy, and I hope that you were busy, okay? And I hope that you were able to. So if you look to the creep, we do have something called the creep curve, and this is what we do in the lab, by the way. Okay, the creep curve. So the creep curve showing the 4 stages. We have something is called initial extension. The moment we apply the load at 0 time, this is time. The creep, by the way, is time versus the elongation. Okay, so this is time versus extension or elongation. Elongation. So the moment that we apply the load at 0 time, you will find there is something deformation will take place. And after that, you keep the load. And normally, that, by the way, for those of you who did this in the lab, we do this for a specimen of lead, because the steel will take many years to get the creep. So we use lead, and the specimen is like this. If you remember from school, we do the lead specimen like this. Creep test. This is lead, because lead deforms a lot. Okay, lead, sorry, make it symmetrical. And we attach it at the top and the bottom. attach it here, fixed frame. Normally I have a frame. I did this in Las Cruces, New Mexico. And after that, we apply a load here, W. Okay, so this is, and normally we make a gauge length here, we make a little tiny mark here and there, and we take this measurement as L sub O. The moment I apply the load P, there is a deformation. This is one, here it is, at 0 time. The moment we apply the load, the frame, you'll find the specimen will elongate or will deform. This is called the initial one. And after that, over time, we start to record the deformation over time. The curve, it will be like this, and after that, the straight line, and the fourth one is like this. We have something called the creep rate. Creep rate. What is the creep rate? A creep rate is the slope of the linear portion of the stage where the creep is almost linear. So the slope of this line is going to give you the creep rate, which is the rise over run. As you know, the slope is the rise over run, which is how many inches per time, and the time is the run in this case. So it's called the creep rate. So this is something, so and a creep failure is also another thing that we need to pay attention to. So this is called the creep, and I needed to be aware of that. So the definition of the creep rate, which is given on the following page. Creep rate. What is the creep rate? A creep rate is the slope of the linear portion of the creep curve, which is the secondary creep, as we call it, which is, so there are 4 portions of the creep curve, and I explain them here, especially the most important thing is the creep rate. What is the definition of the creep rate? And I followed this by a question. Which of the following is not true about the creep rate? Creep rate is the same as the primary creep. Creep rate is the slope of the linear portion of the creep rate. The creep rate is occurring during the secondary creep. A creep rate has a unit of inch per minute or millimeter per minute. That's correct. That's correct. But the statement a creep rate is the same as the primary creep now. So which of the following is not true? So answer A is the one is not true. So I needed to pay attention, and I talk about a creep briefly, as you can see here. But if you need to read more, books are full of. Where is the book here? I don't have it here. No, here it is. This is the one I was using it when I was teaching materials back in Las Cruces, New Mexico. It's a very, very good book also. I'm not selling books here, by the way. Even this book is out of print, as far as I know. They are the testing of engineering materials. This is a book I used when I was teaching, and I wrote a couple manuals for the student back in Las Cruces and also Fresno State here. And these professors are at Berkeley University, by the way, and one from Columbia. These professors are really great, Davis and Troxel and Hawk, These are really good professors, The UC Berkeley, and Columbia University, sorry, University of Missouri, Columbia. It is really, really good, good book. I use it a lot. I use it for about 15 years, this book, or 20 years, I believe. It does have all these things. We talked about all these things. So, and any testing book is good, but I a little bit biased to the books I used in school. So the following one is called fatigue. Fatigue is, if you look to the NCESS, and all of you have this book or a copy of it, which is transportation, the blue book, the NCESS. And if you go to the AM, you will find there is one question, if I remember correctly, let me see if it's still there or not, talking about fatigue. Yeah, here it is, which is question number 133 of the blue book, the NCESS, the blue book, So if you look to the question number 133 of the NCESS, they are saying that fatigue in steel can be the result of, and we are going to see this. So they might ask you about the creep, they might ask you about the fatigue, they can ask you about hardness, which is we're going to see it, they can ask you about impact. All these are the testing that you did in school, and I am here reminding you with all these tests because you might seek some questions related, okay, to these tests. But before I proceed, let me see, there is a question from one of you, and what is the question is, okay, sure, I will do that. Okay, thank you. Sure. So the fatigue. What's fatigue? Fatigue, it is a failure under a repetitive load over time. Fatigue. Okay. Fatigue is failure due to cyclical loading over time. And the first observation from the engineers about fatigue failure, it was observed in bridges. Because, as you know, the bridge, single span, let's assume single span structure, and we have all these trucks or vehicles in general back and forth driving over this. So the member or the members of this structure will do this compression tension, and after the truck leaves, the stress will reduce, and so on. So compression tension, compression tension, compression tension, and so on. And if the structure is a truss structure, do you remember trusses will solve many problems? By the way, trusses, tension, compression, zero force members. I believe we covered this very, very well during this summer. I hope that you still remember all these things. So you'll find there are some members tension, some members compression, and they reverse, by the way. It depends on the position of the load, because the load is a live load, is a moving load. Moving load, loads, okay, moving load. So as the load is moving, the forces in this member change magnitude and also the direction, tension or compression. And this is why, do you remember the IL? What's IL stands for? Influence lines. Is not required for the AM, to the best of my knowledge, except one engineer told me that he saw a problem. I don't know if he can remember very well. I'm not debating his truthnesses, but but the influence lines are not required for the AM, to the best of my knowledge. It's required only for the structure BM. For those of you who are taking structure in the afternoon, they should know how to draw influence lines. And I can show you that for statically determined, statically indeterminate, influence lines for beams, for frames and trusses. Very interesting subject. So because the loads are moving, so when the load is here, is different from here, different from here, so we use the influence lines in order to determine the magnitude of the maximum force in any member. So anyhow, because of this cyclical loading, failure due to fatigue will happening. Like when you have a piece of wire and you are bending this piece of wire back and forth. Okay, if you have a piece of wire, sorry, I don't have a piece of wire. I have only the pre-stress tendons. If you twisting this, sorry, if you bend it back and forth, bend back and forth, over time, or I can take a paper clip and show you that, over time, you will find that the failure will occur, okay, because of the cyclical loading, tension and compression. So this is what I need you to know. So definition of fatigue, okay? What is fatigue? Definition of fatigue. Fatigue is a phenomenon where structures fail when subject to cyclical loading or cyclic loading. This type of structure damage occurs, okay, even when the experienced stress range is below, okay? And normally we express the fatigue that we use a small stress level, but even with the small stress level, still failure will occur because of the cyclical loading. So this is time, and this is stress, and this is back and forth cyclic loading, and eventually the member will fail. Even the stress is stress level is very small. When this truck goes over this bridge, the stresses that will be developed on all these members, they are way below the yield stress. But because of the time, in this case, the failure will occur. And that's why we do have AASHTO, by the way. AASHTO, the American Association of State Highway and Transportation Officials, they have a bridge design manuals. And some of you maybe used it. The bridge design manuals developed by AASHTO, we designed this bridge for certain number of cycles. How many cycles? Okay. Well, there is one equation we use to determine that. Based on the ADT, average daily traffic, the average daily traffic. So the ADT, we know what is the average daily traffic here, and we calculate the number of years the bridge should last. And in this case, we know how many cycles the bridge will be subjected to. And we should design it to be capable of carrying this number of cycles. Otherwise, it will fail. The cracks will start to show up and the structure will fail, even if the stress level is small. But because of the repetitive loading or repetitive application of the load, the structure will fail. So the process until a component finally fails under repeated loading. Can be divided into 3 stages. During a large number of cycles, the damage developed in microscopic level and grows until macroscopic crack is formed. The macroscopic crack grows, okay, each cycle and reach critical length, and after that, the crack components, okay, break, okay, because it can no longer, okay, sustain the peak load. So this is called fatigue. And we do have something, I don't know, a testing machine is called the rotating beam machine. This is a picture of the rotating beam machine. I use this back in Las Cruces in New Mexico. I don't know if you use it in your school or not, but basically this is a motor, and here this is a specimen, and here is the load. So when we put the load, so this is compression, the beam will be like this. This is compression and this tension. But because this is rotating, so the tension side became compression and compression became tension. And we do have a counter to count the number of cycles. Okay, so revolution counter, here it is. So we put the weight, and here is the specimen, and we keep the motor running, and the counter is counting how many cycles until the specimen fails completely. And after that, we change the stress level by changing the weight and so on. And we develop what is known as SN curve. It's very important curve. It's called SN curve. What is the SN curve? SN curve is a relationship between the S for stress, N for the number of cycles to cause failure, and SN curve with defined fatigue endurance limit and without endurance limit. what is endurance limit? Sometimes we call it fatigue limit, by the way. So endurance limit is the same as the fatigue limit. And we need to determine this in the lab. So when we run the fatigue test, it is a relationship between two parameters. The x-axis is the number of cycles, n, and normally this is a log scale, by the way, log, because we have millions of cycles. And this is S, stress level. At very high stress level here, the stress is increasing this. At very high stress, the number of cycles will be a small amount of cycles, maybe a data point. When the stress level starts to go down, you will find that we need more cycles at the stress until we establish this curve. This is called the SN curve. At one point of time, at this stress level, whatever the stress level is, the curve will go forever and never failed. The specimen never fail. So what is the endurance limit or the fatigue limit? This is the endurance limit or fatigue limit. Is defined as the limit of stress at which the material will never fail even with infinite number of cycles. Let me write this down. Okay, so endurance limit or fatigue limit is the limit of stress. Limit of stress where the material or the specimen will never fail even with infinite number of cycles. If you keep the machine running, it will. This, we need to determine that. This is a tangent to this curve, by the way. We call it fatigue limit or endurance limit. Okay. Well, here, there are two curves. The solid one, it has fatigue limit, endurance limit. Here it is. The curve start to decrease until became a straight line. So this, if you come and draw a tangent here, this is called fatigue limit. And we need to know that for this material, by the way. This curve has fatigue limit. The other one, he said without fatigue limit. That means that we are still, okay, getting large number of cycles as we reduce the stress. He did not determine the fatigue limit. But I need you to know the top one. This is with endurance limit and this without endurance limit. So rotating beam machine is very, very interesting machine. I don't know if you use it or not, but I need you to be aware of that. If you look to the following page, additional information about SN diagrams or SN curve for different types of materials. This is the typical SN curve for different materials. Here it is. I gave it the top and the bottom. So you'll find that it starts to decrease, and after that becomes, okay, a straight line. So this is the stress here in megapascal. This is the stress, or this is the fatigue limit, or the endurance limit, as we call it. Question number 9. Fatigue in steel can be the result of the deformation under impact loads? No. Deformation due to overload? No. Expansion due to temperature change? No. A reduction in strength due to cyclic loading? Yes. And this is the answer D. And as I told you, they can come up with many other answers to confuse you. But if you understand the concept, what is a fatigue and fatigue failure, what is endurance limit, and all these things, it will not make any difference. And this is why I always say that I need you to understand the concept, okay? Because on the exam, they are not going to repeat the same question that they were asked before, or maybe some questions available in other book and something like that. No, they come up with the new questions with the new wording, but as long as you understand the concept, it doesn't matter how they ask the question. Make sense? Good, good. Okay. So the third one I needed to be aware of, one test that we do it in the lab also for hardness. There are some empirical relationships. For example, the relationship between hardness and tensile strength is given by this, where B and H is called a Brinell hardness number. Okay, and we are going to see this in just a minute. Okay, so hardness. What is hardness? Hardness is the resistance to penetration. It is measured by denting a material under known load and measuring the size of the dent. So if you have a surface and you would like to determine the hardness, so we have a diamond, okay, like this, a diamond cone, and we apply a load, P. We're applying the load to the surface of the material. So what will happen? This material, because this is normally with a diamond, okay, very hard. This diamond, as you're going to see, it will make a dent, a depth in it. We take this dent as a measure for the hardness, okay, and it is shown on the following page. This is one way of, okay. So what is the definition of hardness? I talked about it. There are different types of hardness. It is scratch, indentation, and rebound. Indentation, the one you are going to see on the following page. And so we have a scratch hardness, indentation, where we create a dent into the material, or rebound. Rebound, they say that if this is the surface, I need to measure its hardness. If I allow a ball, steel ball, to fall from a certain height, okay, this is M, and this is H. As you know, at this level, we do have what's known as a PE. What's PE stands for? Not the professional engineering license, no. Is a potential energy, PE, potential energy, which is mgh. The moment I release this ball from its rest position, it will fall, and the potential energy became what? PE, kinetic energy. And the kinetic energy, as you know, is 1/2 mv squared. Do you remember these things from physics 4a? So this ball will come and hit the surface. This is the surface I need to measure its hardness. This ball will come down, hit it, and it will rebound, will reflect. We take this height, H1, as a measure for the hardness. Imagine that this surface is rubber. Imagine this is a rubber. And you have a steel ball fall from a certain height, it will hit the rubber surface. Do you think this steel ball will rebound? It will bounce back? If this is a rubber, or it will absorb, there is no, because rubber is not very hard, it's very soft material compared to steel. If this surface is a steel or very hard steel, it will rebound. So the ball, it will rebound, it will hit and rebound. This is called rebound, and you are going to see. So I took these 3 basic measurements for hardness and talk about each one separately. Scratch hardness. Do you remember Mohs scale? Mohs scale here, M-O-H, Mohs scale. Okay. Okay. Scratch hardness is a measure of how resistant a sample is to fracture or permanent plastic deformation due to friction from a sharp object. So if we do have something to scratch it, and we can say that if this scratch is going to be deep or not based on the hardness. And we're using Mohs, M-O-H-S. The second one, which is indentation hardness. And this is what you'll see on the following page. There's a diagram. Indentation hardness. So we do have, this is the diamond cone, like Rockwell, by the way, Rockwell test or Brinell test. There are different type tests. Rockwell and Brinell, okay, very common. Vickers also use it. So basically we have this is a surface. This is the surface or the material I need to test. So basically we apply a minor load and apply the minor, okay, plus the major load, which is, so this cone will go down. And after that we release. So we have the minor load left. So in this case, the depth, okay. And the reason that we apply a minor load in order to penetrate just anything on the surface of the material, maybe some scaling or some material. So they allow minor load to penetrate a little bit to eliminate any, or the effect of any surface, okay, imperfections or something like that. So this is called indentation hardness. The following one is the rebound hardness. Sometimes we call it dynamic hardness because we're allowing the bounce. We use the bounce, okay? The height of the bounce of a diamond tipped hammer dropped from a fixed height into the material. We use this as, and I gave you some examples for the rebound hardness. But the second one, by the way, is the most common one, which is the indentation hardness. Indentation, causing some dent into the, or the depth of the indentation. So, and the two questions in front of you here, question number 9 and question, 9.7 and 9.8. Which of the following is not a type of hardness? Dynamic, here we have one. Scratch, yes. Indentation, yes. Ultimate hardness, no. There is no such thing. Okay. And approximate tensile strength for a carbon steel that has a Brinell hardness number of 80. BHN is a Brinell hardness number, is most nearly. As I told you that based on the equations, so the tensile strength in PSI is about 500 BHN, a Brinell hardness number. So if the Brinell hardness number is given, this in megapascal, and this is in PSI. So if the Brinell hardness number was given to be 80, and you need the answer in megapascal or in PSI, so I can use one of these equations. So it is 500 or 3.5. So it is 500, a Brinell hardness number. This will give you the PSI, or a 3.5, a Brinell hardness number. And this will give you the tensile strength of megapascal, and this is in PSI. So if you look to the 80, so 80 times 500 will give you 40,000 PSI. If you take 3.5 multiplied by 80, so in this case, you will find that the number also is very close to one of these, 3.5, 80 times. So it is 280. So this is correct and this is correct. And this is why he said that the answer C, obviously this is the US custom units and this is the SI or the System International. So both of them are correct. This is why I selected answer C. So these are empirical forms must be given to you, by the way. And they are available in textbooks. Okay, I'm not inventing them. These are, as you know, empirical formulas. empirical equations or empirical formulas, equations or formulas. These equations, they develop them after large number of testing, and after that they come up with this kind of relationship. And the empirical formulas very sensitive to units. We have to make sure that we are using correctly because the units are very, very important. Impact test. Impact test also is another test that we do it for metals, for other materials, is to see how much energy can be absorbed, especially for some materials that be used on freeways when a car hits an object or a guardrail or a barrier. We need to make sure that this barrier or this guardrail is capable of absorbing energy. So the impact test, one famous test is called Charpy impact test. There is a picture shown on the following page. The Charpy impact test is used to find energy required to fracture and to identify ductile to brittle a transition. A typical curve is like this. Again, temperature versus energy. And this is the transition curve at the beginning, and after that, as we increase the temperature, the transition is happening, and we determine this in the lab. So impact test determine the amount of energy required to cause failure in standardized test samples. The tests are repeated over a range of temperature to determine the ductile to brittle transition temperature by changing the temperature of the specimen. If you remember from school, and I still have some specimens here, I got these from New Mexico when I was teaching. I have a box of gift or a box of toys I brought with me when I was teaching there, and let me see if I still have them here or not. Okay, I have half of it. Let me see where is the other half. Oh, I have a specimen. Here it is. Here is the other half. And let me see if I can find a specimen for you that is not. So the Charpy impact test it is basically is a notch specimen. I have some additional specimens somewhere here. They used to be next to me here. Here we go. I think I found some. Here we go. I have a lot of toys. Don't worry. Okay. So this is the Charpy impact. This is the Charpy impact specimen. Okay. We make a notch, at a certain depth. This is standard, by the way. And after that, we put the specimen and we hit it from the opposite side of the notch. Okay. And this is, if the notch in the middle, we call it a Charpy impact test. If the notch, it is not in the middle, it's called Izod test. This is like a cantilever beam. We put it like that, and we hit it, as you can see. So there are two tests. One is called the Charpy, and the other one is called Izod, I-Z-O-D. And here it is. Let me show you. This is the impact testing machine. Again, we are raising this hammer to a certain level, H, and we release this hammer suddenly by releasing and the pendulum will swing and it will hit the specimen. And as you can see here, this picture here shows like the specimen, here it is. The specimen, okay, this has the V notch, and we hit the specimen from the opposite side, and we have a scale here where this scale will give us the energy absorbed directly. Okay, so this is the Charpy. There is another test is called Izod, IZOD. Also is a measure for the, and this when the notch is not in the center, we put it like a cantilever. Here it is. This is like a simply supported beam. This is simply supported beam. It is supported from here and it's hit. So this is simply supported beam. But this is a cantilever as cantilever on. So this is the striking direction. So it comes and hit it that way, and it will ensure the failure. The reason they created a notch to ensure that the failure will be at a specific location. And we compare the amount of energy by taking the reading directly from the scale. And the effect of temperature on the Charpy toughness, we can also increase the temperature and look to the impact, and it can be okay, a brittle type failure and ductile type failure. Do you remember the ductile and the brittle type failure? Here it is. This is the ductile fracture or type failure fracture, and this is a brittle behavior fracture or ductile behavior, and this is a brittle behavior. So I needed to be aware of that. The impact pendulum testing machine, a Charpy and Izod impact tests. Okay, and this is after failure. By the way, the specimen I showed to you, this one here, this is the Izod one. It was like this. It was a V. Let me see if I can assemble it again. Hopefully I can. Yeah, here it is. My God, sorry. Let me. Here it is. Here it is, like that. It was a V. Okay, and the specimen was hit here, and this is a fracture after has been okay tested in the lab. So question number 99. Okay, impact strength is defined as ability of the material to absorb energy, the potential energy of the pendulum, the resistance to cyclical loading, deflection under impact load. Obviously, the answer is A. The ability of the material to absorb energy under impact load. Okay, we don't measure deflection. Yes, under the impact load, the deflection will occur, but we don't measure deflection, we measure energy. So very important that this, okay, and I believe it should be mentioned at the beginning, and here it is. If you look the definition of impact, but can you go to the previous page? Probably on page 13, please. Page 13. What is the definition of impact? It is the ability of the material to absorb energy due to impact load. Here it is. This is something very, very, I will highlight this. Okay. So please look to this test, and the following section is talking about concrete. And I know I talked about concrete during the workshops. I don't know when, and we solved some mixed design. We talked about testing for concrete, and we mentioned a lot of things, in fact, during the summer workshops. I hope that all of you attended, and the concrete, as I said that, so concrete either non-reinforced or reinforced. But in general, and the question, by the way, they have 1 or 2 questions in the AM section about concrete. Here it is. By the way, let me go back again to question 133 of the blue book. Okay, if you look to the blue book, okay, you have one, the coiled one. You have the coiled one, small one. Okay, because okay, so no, okay, small one. If you go to question number 133, okay, 133 on page 27, okay, you will find this is a fatigue question. And this is my explanation about the fatigue test and so on. And it is a reduction in strength due to cyclic loading. Here it is. And this is the SN curve. Do you remember the SN curve I talked about it? So I needed to remember that. On the same page also you'll find this. A question related to concrete. Let me give you 1 minute to look to this question and tell me what do you think. And for those of you already, because we covered this before, so try to be patient with your friends for those who are seeing the question the first time. Question number 132 of the blue book, not the Kelly blue book. Kelly blue book, this is for cars, but this is a blue book for the PE. Okay, this is an easy one, but as I mentioned before, and I will repeat this again 1 more time, that the type of questions they included in the practice exam, the NCESS, this is the NCESS book, as you know, unfortunately they include very easy questions. So these questions are so easy compared to the actual exam. This is what I heard from the engineers who took the exam before, and this is a true statement to the best of my knowledge. So we need to prepare ourselves way beyond the level of difficulty of these questions, because the questions are really difficult, okay, compared to these questions here. I wish that they did the opposite, as I mentioned before. I wish that they gave us difficult questions here and we see easier questions on the actual exam, but this is the case and this is what is happening. So don't say that since I know these questions and I know how to handle them, I will be able to pass easily. No, I don't like you to assume that. Assume that the level of difficulty or difficulties of the questions on the actual exam will be way more than what is given here. Okay, I'm not trying to scare you or try to frighten you, or I don't like to say that Dr. Mansour spread fake news. No, I'm not spreading fake news. I'm just telling you what I heard, and I hope that. Okay, so concrete as a construction material that was used way back by my grandfather and your grandfather. They mixing concrete for a long time. So we can look to concrete from different perspectives. Concrete as a good construction material. We can look at it as a plain concrete or reinforced. This is one classification. A plain, it has no reinforcement, like the slab to put it in your backyard, probably just a 3-inch or 4-inch slab, 4-inch normally, 4-inch slab thick. You compact the soil very well, and you put the concrete slab just for something on your backyard or sidewalk and something like that. We don't reinforce it, generally speaking. Some people, they put the wire mesh, but generally speaking, just as a plain concrete. Okay. The other one, that we do have a beam, and this beam is going to carry load, so we need rebars. So we reinforce it. Okay. For main steel and shear steel. Concrete could be looked at also as lightweight and normal weight. Which the unit weight in this case, gamma, is going to be affected. Gamma for lightweight concrete is about maybe 70 to maybe 90 pound per cubic foot. Very wide range, by the way. There is no any well-defined. But normal weight concrete gamma is between 145 to 150 pound per cubic foot. So it's normal weight versus lightweight. This is another way of classifying concrete. Another way we can look to the concrete as air entrained versus non-air entrained. Air entrained versus non-air entrained. We can look to the concrete as a pre-stressed or the non-pre-stressed. And the pre-stressed concrete, by the way, pre-stressed concrete, there are two types of a pre-stressing concrete. Post-tensioning and the pre-tensioning. Post, I will, and the pre. So concrete, you can look at it from different perspective. And we need to be ready such that we are familiar with the different types of concrete. For the AM, I'm talking about the civil AM portion, the AM portion. Nobody will ask you to design a beam. I never heard, I can go over this in the class, but B and D and the area of steel and the amount of the many, I never heard about that. Some vendors, they cover this to the best of my knowledge, and some books, they have it. review books, but to the best of my knowledge is not within the NCESS exam specifications. But for the civil AM, we should know the types of concrete, the difference, all these types we talked about. We should know how to testing concrete, and testing concrete, it should be also covered under 2 while the concrete is fresh and while the concrete is hardened. Hardened concrete and the fresh concrete. You should know how to perform testing. Types of concrete, which all these types I mentioned before, you should know the difference between this and this and this. And you should know for the AM, again, I'm still talking about the AM, this mixing of concrete. Under mixing of concrete, there are 2 methods you should be familiar with, which is the ratio method and the absolute volume method. Absolute volume. Also, we can look to the design of concrete members. But here the design of concrete members, not to design the member itself. He will not give you a column until you design this column for me, or tell me how many rebars are required for a column or for a beam or for T-section and so on. But what are the parameters should be considered in design? Parameters will affect how the member will resist the load. He will not ask you, okay, I will not, okay, ask you to design a beam, but you should know where we should place the reinforcement and why. And we'll talk about this in depth. By the way, I have many figures and illustrations in my books. For example, a famous figure from the CRSI. The CRSI, if I remember correctly, let me see if I have it here or in the other book. So the let me see, I believe it is in the other book. Or do you know what? It might be at the beginning of chapter 3. Sometimes I mix my, sometimes I, if it's not here, so it's a very important figure. Normally I go over it. Let me see if it is. I know it is shown in the textbook as part of the discussion of the rebars and so on. If I am not able to find it right now, no problem. I will find it later on and show it to you. It is a very common figure. Probably you saw it before. We're talking about the position of the rebars. I was under the impression that it is here, but I might mix it with other. So anyhow, it is one of the figures that the CRSI, the Concrete Steel Reinforcing Institute, I believe, if I'm not mistaken, and I remember now where it is. I think it is in the maybe it is here for the here it is. Yeah, I remember right now. Sometimes, okay. Yeah, this figure here is here it is. As concrete CRSI, the concrete reinforcing steel institute, is very important, and it does have different types of members. I'll be glad to scan it and send it. Those of you who do not have my textbooks, I think they are available everywhere in my textbooks, but this one here for sure, and the other one. But for the summary book, probably for the exam book, practice exam book is not there. And we need to make sure that you are really knowing exactly where things, because during the exam you have no time to go and look for an index. You should know exactly by heart, like this, like the one I just talked about it. I know where is this. This I put it here, and I put it here, I put it here, and I try to, and by practice you will be able to find all the information that you are looking for, and something very. So we should know. He will not ask you to design any of these member, but we need to know where are the rebars and why you are putting the rebars at this position, and what is the purpose of placing the rebars, and so on. When we come to mixing concrete, we should know the ratio method. Ratio, the one that my grandfather and your grandfather used, which is 1 to 1.8 to 3.5. This is called a ratio method. A ratio method. Okay, a ratio method. Okay, where the concrete is mixed based on that ratio, like the problem given in the NCESS in one of the books, in the construction book, I believe. They gave some problems, and they have. So the first one is referring to the part, how many parts of the cement, and they're using 1. And the second number is a fine aggregate, aggregate, and the third one is a coarse aggregate. And I discussed this in chapter 7 of my textbook in depth, which is also given here in the handout, as I'm going to show it to you. Okay, chapter 7, talking about all these things, mixing concrete, and they put it in a table form. Here it is, the absolute, the ratio method, okay, and the absolute volume method. This is 1 to 2 to 4, for example. The first one is cement, and the second one is fine, and the third one is coarse aggregate. So we need to know that. And also, I believe in the handout I gave you, or this chapter here, the one I send it to you, I believe it does have all this, by the way. It does have all, it has tons of problems. Okay, you see testing the beams, okay, for plain concrete and for reinforced one. And why with this is a pre-stressing, by the way. Here it is, and here it is, by the way. I included the table that from the CRSI, so it is here, so you have it, so I don't have to send it to you. So in chapter 9 you have it. So it seems to me that you have, to the best of my knowledge, you have a lot of material, timber, you have asphalt, you have concrete, you have mixing, a lot of things that soil also, compaction, as a lot of, and finally you have about 49 problems. So the only section that I don't expect that will be for the PE is the last section of this handout, but I wrote the equations just in case, which is the thermal stresses. Okay, thermal properties. The last on page 70, I talked about thermal properties and thermal stresses. Okay, and the two equations that we normally use, okay, which is the deformation and the stress. And I have a problem 949. So you have about 49 problems in this chapter. This may be the only problem that I say this is a purely FE, okay, not PE, But since you have it, I will put this in the 3-inch ring binder, and I recommend that everybody start to build your 3-inch ring binder. For those of you who already started, that's good news. And try to put the material in order, and you should know exactly where the material is located and what information included in each one of them. So the concrete itself as a subject is a very huge subject, and I'm sure that during your school time that you learn all these things, and I will do my best, okay, in the future if I can. So I needed to know the slump test, how to do the slump test, how to mix concrete. Mixing concrete is important. Equations, I provide you with the equations. Uh, and I did my best. Compaction also is very important. Compaction, the Proctor test also, it is here. A Proctor test also, we cover this under materials. So a lot of stuff. I will conclude by this diagram. I came up with this diagram, which I drew it before many times. This diagram is important diagram, and we use this diagram twice. One for concrete mixing and one for the soil. So let me conclude this discussion by referring to two illustrations. I drew them before, by the way, which is the earthwork, because some of you are attending today the first time earthwork. So for earthwork, we have three status of the earthwork. We have the bank cubic yard, and loose cubic yard, and compacted cubic yard, CCY. And all these definitions are given, so you are familiar with it. And as I mentioned before, from the bank cubic yard to loose cubic yard, we have a factor. We call it a swell factor. And the swell factor is equal 1 plus a swell percent. And this factor is greater than 1, by the way. The other factor, which is from the bank cubic yard to compacted cubic yard, is called the shrinkage factor. Which is equal 1 minus shrinkage percent. And the swell percent and the shrinkage percent must be given to you in the problem statement. You cannot assume it. There is a range, and I have a table shown on my books based on the textbooks, the range, the common range. The shrinkage factor, by the way, generally speaking, is less than 1 for sand, silt, clay, gravel, or a mixture of any of these soils, but is a greater than 1 in one condition for rocks, because rocks will never shrink. Rocks, okay, in fact, they increase in volume after we blast them, after you do blasting. You cannot put the concrete pieces again as God created originally, so they will occupy more volume than the original volume as they exist. This is why the shrinkage factor is greater than 1 for rocks only. We need to know how to do this transition from here to here or from here to here, because the earthwork or the volume computations, earthwork or volume computation is very important, and expect some questions on the exam related to this. By analogy, okay, I came up with this curve to illustrate all this, because instead of developing equations, you can see the picture how this is related to this. And I have equations, by the way, written, okay, also in my books. The second diagram that similar to this in the sense of concept is concrete design, concrete mix design. Also, we do have three circles as shown here. One is here and one is here, or oval if you like to call it oval, is not. And the first one, or let me start with the middle one. We call it SSD. SSD, we use it twice, by the way. We use it here as saturated surface dry, or for transportation, we use it as a stopping side distance, SSD. So the SSD does have the abbreviation SSD is, it has two definitions, but here is a saturated and surface dry condition. Saturated and surface dry for concrete mixing topic. Below the SSD, we call it dry. Above the SSD, we call it wet / moist. Also, the aggregate, let me see if I have a piece of aggregate. Here it is. And this also came from Las Cruces, New Mexico. Can you believe that? This piece of aggregate came from all the way from New Mexico when I was teaching there. This piece of aggregate, it could be either at the SSD, which is a perfect condition or ideal condition, or this is the base condition. The base condition that for our design, normally we assume that the aggregates are in SSD, either coarse aggregate like this or sand. Sand is a fine aggregate. So the SSD is a base condition. If you are below the SSD, that means that this aggregate is dry. It dry, that means that it will absorb water to reach from here to here. And we call this is SSD moisture. Percent. And this should be given to you in the problem statement. Don't assume it. But from here to here, when you have a dry coarse aggregate, to reach to the wet or the moist, or if I have a moist and go to the dry, we call this is the moisture content. So there are two types of moisture. The overall moisture content, we normally, by the way, in soil mechanics, we use lowercase w, which is the weight of the water over the weight of the solids. This is a definition of moisture content. Moisture content or water content. Some books, they call it water content. Water content or moisture content. So from here, and we should know how to calculate the weight here, the weight here, the weight here, and so on. So if we understand these relationships, wet or moist, okay, and I illustrated this, by the way, in a diagram. Here it is on page 34 of the handout. This is the SSD, which is the perfect condition, saturated and surface dry condition. The aggregate is saturated, but the surface is dry. Below the SSD, we have the dry, either air dry or oven dry. Here we need to add water. It will absorb water to reach from here to here. But if it was raining yesterday and I have the aggregate that's wet or moist, so this is above the SSD. but our design must be based on this SSD. And I came up with these equations. And by the way, all this I did not invent it. Don't think that when I say I came up with these equations, I did not invent them. I am presenting them. But the basis for all this, by the way, very nice book by PCA, Portland Cement Association. They have the 15th, or right now the 16th edition. I believe this is a 15th edition. Here it is. This is Design and Control of Concrete Mixtures. This is the 15th edition by PCA, Portland Cement Association. This is one of the references, by the way, for the transportation group. Transportation, they have 12 references. This is one of them. It's a very good book. They have the 16th edition right now, color and nice. And I use it when it was way back, the first edition, by the way. This is way back when I was teaching back in Las Cruces, New Mexico. It was the first edition. Right now is the 15th edition. Okay, so it was very simple book, but they keep adding and improving properties of concrete and test design, and it's a very good book. So I am using textbooks to develop my own review books for you guys. So any equation you see or any table or chart or illustration is not my invention, but it is a presentation of material available from other materials. How to present it. Knowledge is knowledge. I'm here to present the knowledge, and I hope that I succeeded in doing that. Okay, I will stop here, and again, I will thank all of you. I will scan these things and send it to you. For those who attended today, I will get your attending list today from the webinar company, and I will send it to you. And I hope that you enjoyed this summer with me. I hope that you learned something, and I hope that you are ready for the exam, and I wish you the best. For those who are going to join me in the classes, one is tomorrow, the transportation, and we will continue, and the next week will be the AM, and proceed all the way to October exam. And I hope that I will be successful in achieving your ultimate goal, which is the PE, which I've been doing this for almost 30 years. And a lot of engineers, thousands of engineers, they got their PE with some kind of help from me. But the ultimate decider about that is you. Without studying, forget it. There is nothing that's called a luck, or maybe I will pass the exam without the preparation. No, I always say that you need to put at least a minimum of 500 hours for the AM plus PM, whatever your PM is. You need to sit and study. You need to sit and solve problems. You need to sit and make mistakes. And the more you solve, the more you make mistakes during the preparation, the easier for you during the actual exam. And I wish all of you the best. And thank you again for joining me this summer. And I wish the best to all of you. Communicate with me, and I will do all my best to come back to you as soon as I can. And forgive me if I didn't come back to you immediately. I know your time is very valuable, but I will do all my best to help you as much as I can. And I hope that you will take the exam this coming October. They will not cancel it as some rumors or some fake news. They announce it. And I hope that this will be the last exam you take it. Okay, for the PE, obviously you can go to the SCE after that. And I wish you the best, and forgive me if I said anything that I don't mean to offend anybody. Sometimes I tell a little bit of jokes to keep you awake, but I don't mean to offend anybody either politically or any other ways. Okay, so thank you very much, and enjoy the rest of the 4th of July. You can go right now to prepare for the fireworks with the kids and the family, or you go and watch it somewhere, as long as you are going to keep a safe distance between you and your neighbor. And I wish you the best. Stay healthy, and thank you again, and good night. Bye-bye.